Hello viewers, welcome back to the course on matrix computation and its application. So, today lecture we are all going to discuss few more applications of the statement that the null space, if the null space of the matrix A is only the zero null space, then the corresponding matrix, if it is a square matrix, is a non-singular matrix. So, that we are going to take the application based on this one. So, let us do that. So, today we are going to discuss about one more term, and that is very useful these days. So, now suppose we have data. Suppose we have data points. Let I just take x and y axis, and suppose I have some data points are given to me. So, these data points can be anywhere, and suppose this data I can write as x1 y1, it is x2 y2, x3 y3, these are the coordinates, and this is suppose xn yn. So, in this case suppose I have m number of elements. So, suppose we have the data points, that is x1 y1, maybe I can write x1 y1 x2 y2 xm ym. So, m number of points are there, number of points. So, this is the data points are given to us, and now suppose I just want to interpolate these points with the polynomial. So, now what I do is that I just take a polynomial passing through this point. So, suppose this is the polynomial, I suppose I have going from here, then reaching here, this one, suppose this is the point here. Suppose this is not the point, it is just maybe this point is there. So, let us suppose I have this number of points, and I take a polynomial that is passing from these points. But some student says that I can draw another polynomial, not like this one, maybe I can have a polynomial like this one going from here, then this one passing through all points, and then this one. Maybe some other students can plot another polynomial like this one, this polynomial. So, by this way we can have a large number of polynomials we can show, and which is passing through these points. So, based on this one I just give you one statement that given a set of m points. So, I take the set S as points are given to me x1 y1, it means this is my corresponding x1 and this is the point corresponding to this, so that is y1. So, x1 y1, x2 y2, and this is xm ym. So, m number of points are there given to me, in which each xi is not equal to xj, means all points are distinct. This is my x1, this is corresponding to x2, this is maybe x3, and this is the last one is xn. So, all my xi's are different, we know that one. It means we are taking the point at this point and this point and this point only once, never 2 times. So, that is we are taking. Then, so we give the statement, then there exists a polynomial, or maybe I can say there exists a unique polynomial that I write as a PT as alpha 0 plus alpha 1 t alpha 2 t square up to alpha m minus 1 t m minus 1 of degree. So, its degree is m minus 1, that passes through each point in S. So, it shows you that first thing is that we are going to have a unique polynomial and its degree will be always m minus 1, because we know that we suppose we have a 2 points, then we can have a line passing through this one. So, it is of degree 1. When we have 3 points, suppose I have 1, 2, 3. So, we can have a quadratic polynomial from this one. So, we have 3 points, but it is going to have a only quadratic. So, we have m points, we are going to have a unique polynomial of degree m minus 1. So, this is degree m minus 1 that is passing through all points. So, from here one thing is clear, that we have drawn 3 different type of polynomial, but by this theorem we are going to show that only one polynomial, that is a unique polynomial, is going to pass through all this point. So, this one we are going to use now. So, the proof of this one. So, in this case we are going to have a unique polynomial. So, given that polynomial at x1 should be equal to y1, because it is passing through this point. So, passing through means point, that if I take p x1, then it should be equal to y1, which implies that alpha 0 plus alpha 1 x1 alpha 2 x2 alpha 2 x1 square alpha m minus 1 x1 m minus 1 should be equal to y1. Similarly, because it is going to pass through all points, so given that given PT is passing through all points, it means that Px1 should be equal to y1, Px2 should be equal to y2, and Pxm should be equal to ym. So, from here I can write as alpha 0. Another equation I can write as alpha 0 plus alpha 1 x2 plus alpha 2 x2 square alpha m minus 1 x2 m minus 1, that should be equal to y2. And similarly, I can write the last one alpha 0 alpha 1 xm alpha 2 xm square alpha m minus 1 xm raised to power m minus 1, that should be equal to ym. So, this is we are going to have. So, this is basically, if you see, it is a system of equation. So, from here I can write this system as 1 x1 x1 square, x1 cube, in the last I can write x1 raised to power m minus 1, 1 x2, x2 square, x2 cube, x2 m minus 1. So, this is the way we can write the corresponding matrix. So, it is x1, then xm, xm square, xm cube, xm m minus 1, and this is alpha 0, alpha 1, alpha 2, alpha m minus 1. So, this is a m cross m matrix, and this is m cross 1 matrix, and that is equal to y1, y2 up to ym. So, I going to have a system. So, I just write this as equation number 1. So, now if you see from here, this corresponding matrix, so it has some special name, and that is, its matrix is called Vandermonde matrix. Okay, so and represented by V. So, it is just the matrix 1 x1 x1 square like this one. So, it is called the Vandermonde matrix, and suppose this alpha I just write as maybe some capital alpha, and this is I can write as B. So, I get the system V alpha is equal to B. So, that is the system we are going to have. Now, I am going to show that this is a unique one. So, this polynomial is unique. So, this polynomial is unique means the solution of this system should be unique. Now, for the system 1 to have unique solution, we have to show that the matrix V is non-singular, because if it is a non-singular only, then we are going to have a unique solution, that we already know from the matrix theory. So, which implies that we need to show that null space of the matrix V is just a containing the 0 element. So, this is equivalent to saying that null space of V is equal to 0, that we have already seen in the previous results. So, now we are going to show these things. Now, what are you going to have? So, I want to show this thing now. So, let us write. So, we can have corresponding homogeneous system as V alpha is equal to 0, where V is this matrix and alpha is this value. Now, from here we have, so V alpha is equal to 0. So, from we can write from here that, and alpha is made up of this alpha 0, alpha 1, alpha 2 like this one. So, from here I can write we have, or maybe we can write, so I can just write is 2 system 2 as. So, I just write the first one. So, first one will be alpha 0 plus alpha 1 x 1 plus alpha 2 x 1 square up to alpha m minus 1 x 1 m minus 1 equal to 0. So, this is the first equation. Okay. So, similarly, now this is the first equation I am going to write. So, this is the first equation I am writing now, which implies, if you see from here, that I am putting the x 1 in the given polynomial and getting the value equal to 0, which implies that p x 1 is going to be 0, which implies that x 1 is a root of the polynomial p t. So, this is the polynomial I have p t. So, that the polynomial we have defined this one, and it is going to show that x 1 is a root of this p t by this way. So, similarly, we can show that alpha 0 plus alpha 1 x I alpha 2 x I square alpha m minus 1 x I m minus 1 equal to 0 for I is equal to 2, 3, 4, sorry 2, 3, 4, and this is going to be up to x m, which implies that x 2, x 3, all x m are the roots of the polynomial p t that we have defined. So, from here, so one thing is true, that since the polynomial p t is of degree m minus 1. We know that the polynomial is of degree m minus 1, but it has distinct, it has, so you can see from here it has m distinct roots. It is of degree m minus 1, but it is having m distinct root, that is x 1, x 2 up to x m, that we have showed from here, this one. But that we know that by the fundamental theorem of algebra, that guarantees that if p t is not a 0 polynomial, then p t can have at most m minus 1 distinct roots, because if it is of degree m minus 1, then it can have a maximum m minus 1 distinct root. So, which implies that my p t should be 0 polynomial, but that is not the 0 polynomial. We have taken this one passing through this point. So, which implies that this is the only possibility that alpha 0, alpha 1, alpha 2, all this alpha m minus 1 should be equal to 0. So, it shows that this polynomial should be equal to 0 itself only, and which implies, so if all these alpha i's are 0, then from the system 1, from the system 2 I can say that, which implies that V alpha is equal to 0 gives you that alpha belongs to the null space of V, because it is going to 0, and null space of V contain only 0 element, because definitely alpha will be definitely in the null space of V, and the values I am getting alpha 0, alpha 1, alpha 2, all these values I am getting 0. So, null space will contain only this element, only 0 element. So, that implies that the corresponding matrix V is non-singular, and if it is a non-singular matrix, so which implies that V alpha is equal to B is going to have unique solution, and that solution I can write as V inverse B. So, if it is going to have a unique solution, it means the alpha i's we are going to get in this case are unique. So, from here I can say that my polynomial Pt is unique. So, whatever the points you are taking, you can draw different polynomials, but from by this theorem we have shown that only a unique polynomials is going to be that passing through all the points. So, that is the proof of this one. So, this polynomial will be unique, and this polynomial you can find with a different way, but this is going to be unique if it is passing through all the point. So, that is one of the application of this property of null space containing, null space is going to be only 0 space. So, this is one of the application we have taken. Another application I want to apply, I want to show you. Now, so this is the application we are going to discuss. Suppose I take, let I have a vector space V is a vector space of real valued functions of a real variable. And let I take a set S which contain n number of functions coming from this one. So, be a set of functions that are n minus 1 times differentiable. It means that each f I x belongs to the vector space V and n times and n minus 1 times differentiable. So, that is the meaning of this one. Okay, so, and the set S is there. Now, so then Then there is a word term Wronskian, or we also some books write like a Wronskian. Then the Wronskian matrix or Wronskian matrix, so that this is the matrix we are going to write, f1x, f2x, fnx. So, I am going to write this matrix with the function. Second row is just the derivative, taking the derivative of each function, and similarly I can go and I can take n minus 1 time derivative and writing in the same column. So, I get this matrix, it is n cross n matrix, and we call it Wronskian matrix. So, this matrix I have written. Now, so now the statement, this is what we are now. If there is at least one point, that is x is equal to x naught. So, x is basically x belongs to some interval in the given domain. So, this is a statement, if there is at least one point x equal to x naught such that the value of the Wronskian at x naught. So, x naught at x naught, it is just a matrix of numbers. So, is non-singular, then the set S is linearly independent for all x. So, this is my statement. S means statement, that what I am going to do is that I take a vector space and suppose that vector space is made up of functions, and suppose I take a set S and somebody asks me, okay, tell me whether this set is linearly independent or dependent. Then how we are going to check whether this set is linearly independent or dependent. So, this is what the way we are going to do. So, and in this case we are finding that these functions are n minus 1 times differentiable. Then we have written the Wronskian matrix, and then we say that if I choose any point, only one point x equal to x naught, and I found that at this point this Wronskian matrix is non-singular, then just I can say from there that this set S is going to be linearly independent. Okay, so that is the powerful way, that only one point, if it is satisfying, it is satisfying for all. So, this one we are going to prove. So, let us do this one, proof. We basically want to prove that the set S of the function f1x, f2x, fnx is linearly independent. So, this one we want to show. Okay. So, suppose I have a function and I want to show the linear independent. So, which implies that I will take some scalars, maybe I can write alpha 1 f1x, alpha 2 f2x, alpha n fnx is equal to 0. So, this is what I have taken the linear combination putting equal to 0. So, this is my linear combination and I am putting equal to 0. So, this one we have taken. Now, after doing this one, so this is my, maybe I can write this is equation number 1. Now, how to prove this one? So, I will already do differentiate equation 1 n minus 1 times with respect to x, because I have assumed that my functions are differentiable and it can have n minus 1 times differentiable function even. So, I can write here f1 dash x plus alpha 2 f2 dash x alpha n fn dash x equal to 0, and I can write alpha 1 f1 n minus 1 times differentiable, alpha 2 f2 n minus 1 the derivative, alpha n fn I am taking n minus 1 time derivative of this one, and that is also coming 0. So, from here I can write this system as f1x, f2x, fnx, okay, f1 dash, f2 dash, like this one fn dash, I am just writing. So, it is understood as a function of n, and from here I can write f1 n minus 1 derivative, f2 n minus 1 derivative, and fn n minus 1 derivative, and I can write from here alpha 1 alpha 2 alpha n, and this can be 0 0 0. So, this system I write is 2, and now from here this can be written as, you can write from here that this becomes a Wronskian matrix. So, because this is a Wronskian matrix and this is a alpha, so I can write as a alpha equal to 0. So, this is a system I can write as a 3, equation 3, where alpha is basically alpha 1 alpha 2 alpha n. Now, so it is given to me, now given so from here it is a homogeneous system. So, homogeneous system is basically, from here I can write that alpha belongs to the null space of Wronskian matrix. Also, now it is given to me that for x is equal to x naught, alpha will belongs to the null space of x naught, because it is true for all x. So, if I choose just x equal to x naught, then definitely alpha will be there, but null space of is just the 0 element. It is written from here that if there is at least one point where this matrix is non-singular, so it means if it is a non-zero, it means that the null space of this is going to have only one element. So, which implies that my alpha should be 0, and which implies that my alpha 1 is equal to alpha 2 up to alpha n all should be 0, and if it is 0, then it shows that the function f1x, f2x, fnx are linearly independent for all x, because here we are representing with just one point, and then it shows that the alpha 1, alpha 2, alpha i's all are 0, and this is the linear combination I have taken, and from this linear combination we found that alpha 1 alpha 2 all are 0, and it is true for all x in this case now. So, from here I can say that this is linearly independent for all x. So, which shows that S is linearly independent set, and that is true for all x. So, this way we can prove the set of functions whether they are linearly independent or dependent. So, after this we will stop here. So, today we have discussed two important applications of the statement about the null space, zero null space corresponding to the given matrix, and we have showed that the interpolating polynomial for the given data is always unique, and then we have showed that how we can check the given set of functions to be either linearly independent and dependent. So, I hope you have enjoyed this lecture. Thanks for watching. Thanks very much.